We're going to take our treatment of blackbody radiation just a little bit further now by looking at the Sun. So we're going to deal with the Sun as being a blackbody radiator, and you'll recall from the previous video that we said that blackbodies are idealized objects, so they don't actually exist. But the Sun and other stars are fairly close approximations, and when we consider the Sun as a blackbody radiator, just under half of its radiation is visible light. So all of the energy being radiated from the Sun, half of it is stuff that we can actually see, and a similar quantity is in the infrared region, and the remainder is in the ultraviolet. And so that's about 10% is ultraviolet. So there's the spectrum from the Sun, and all of that energy is it's quite a significant amount. So the Sun emits very large quantities of radiation. And if you think about the Sun, big sphere, it radiates that energy in all directions. And what that basically means is that only a small percentage actually arrives on Earth. And so all of the energy radiated by the Sun, the majority of it is sort of out into space, and so there's very small proportion arrives at the top of Earth's atmosphere. So that's the basic idea that we need to consider when we're looking at this quantity of the solar constant. So the solar constant, to go through and explain a little bit more clearly what it is the amount of solar radiation, so all of the radiation from the Sun that reaches Earth, but we need to consider that it's across all wavelengths. And need to be a little bit clear as well about how long. So it's the amount of energy in 1 second, and if we're talking about the amount of energy in 1 second, we're really talking about power, and we also need to identify what sort of area we're dealing with, and that will be 1 square meter. Finally, we need to consider the fact that as the Earth moves around the Sun, it's not a constant distance from the Sun, so there's a bit of an elliptical orbit, but we'll consider it as being the mean distance of the Earth from the Sun. And that, when we're talking about that area, just to really nail this down, that area is on a plane perpendicular to the line joining the Earth to the Sun, or joining the centres. So a fair bit of detail in that explanation, but the reason we need is to be very clear about the constraints around this idea of the solar constant. So just to explain it a little bit more clearly in terms of a diagram, imagine that we've got the Sun here radiating energy off in all directions. So you can imagine sort of these rays of energy being radiated. If we have the Earth somewhere over here, where we've got this mean distance from the Sun, we would then consider, so if we look at a small section of the Earth's atmosphere here and kind of look at it in a larger scale, so we'd have 1 square meter, and it's the radiation passing through that 1 square meter in 1 second. So a fairly specific amount, and if we look at all of the radiation from the sun, we can identify that of the 4 by 10 to the 26 watts of power radiated from the sun, there's only a very small quantity that would correspond to the solar constant. So at the Earth's distance, and that distance that we're talking about here is 1.5 by 10 to the 11 meters, only about 1,366 watts per square meter is received by Earth's atmosphere. So you can see that it's a very, very small percentage. Now, while that's taken as a constant, it's a little bit misleading to use the word constant there, because it does actually vary. And we need to consider the fact that there are a few contributing factors. So the value of the solar constant does change. And so 3 reasons that we're going to have a look at. And the first one is the fact that the sun's output is not necessarily constant. And so the reason for that is the one of the cycles in the sun being its sunspots. So the output of the sun can vary by about 0.1% over its 11-year sunspot cycle. Now, it might not sound like a lot when we're saying 0.1%, but when you're talking about the quantity of energy that the sun radiates, that does end up being quite a lot in terms of the total energy, and therefore the impact that it has on the energy that is received by Earth's atmosphere. The second, as I mentioned, is the elliptical nature of the Earth's orbit. So the elliptical orbit of Earth means that it's going to be closer at some parts of the year and further away at others, and typically it's closer in January. So closer to the sun in January, and further away in July. And the effect of that, being the solar constant, can vary by about 7%. So 2 contributing factors to the way that the solar constant can change. The last one's a little bit more vague, being that there are potentially other longer period cycles that occur in the sun. So talking about the magnetic fields in the sun and those sorts of things that we're not entirely sure about, because our observations of the sun haven't necessarily been long enough. So there's other sort of contributing factors that are still sort of yet to be determined. Now, there's one other aspect of the solar constant that I want to delve into, just to try and clarify something that might pose problems later. When you think about solar radiation being received by the Earth, it ultimately is going to be determined by the cross-sectional area of the Earth itself. So if you would imagine shining a light on an object, the light that it's going to receive is determined by the cross-section, not so much the 3D nature of the object. And so for the Earth, being a sphere, its cross-section is a circle that's given by pi r squared. But that energy is actually distributed over the surface of the sphere. And so we've got a slight difference in those two considerations. And the reason why it's distributed over its surface is that the fact that the Earth rotates, and so we see that the area in that case is the surface area of a sphere, which is given by 4 pi r squared. And as a result, the solar constant doesn't actually reflect how much energy is received on the surface of the Earth, and we can then identify that the average incoming solar energy is actually 1/4 of the solar constant. And you can see there between those two area calculations, the difference there is the factor of 4. So the cross-sectional area relates to the solar constant. The surface area relates to the energy that's actually received by the Earth. And so given that the solar constant has a value of approximately 1,366 watts per square metre, across the Earth, energy is received at approximately 341 watts per square metre. So a factor of 4 difference between the solar constant and the average incoming solar energy as measured on the surface of the Earth itself.